Okay, so today we're going to continue our discussion of Bell's theorem and non-locality, preferably in a much more concise way. And then we'll turn to a discussion of pathological formulation of quantum theory. In the context of so what we're going to do within Bell's theorem I want to revisit. Here, I'll give a concise version of the proof. And then I want to discuss a quantum information theoretic perspective on this. So clearly, Bell's theorem is of interest in foundations to understand something about the nature of reality. But it's important to realize that it's also interesting from the quantum information theory point of view because it's a resource that we can use to achieve things, solve practical problems that we otherwise don't have access to with classical physics. So I'm going to introduce the CHSH game. And then I'll discuss the idea of entanglement versus non-locality as a resource. Okay? Okay, so step one is we'll look at a slightly different proof technique, which I think was more accessible. Okay, so we're going to introduce a slightly different notation. So we're just going to refer to Alice and Bob. Alice has measurement settings A0, which we were calling A in our previous lecture, and A1, which we were calling A prime. This is just so I can have a more concise notation. And outcome X, which we'll just call 0, 1. I think that's what I'm doing. And then, or is it plus minus 1? Oh, actually, yeah, we're allowing the continuous interval. Sorry, that's the point. Minus 1 to plus 1. Similarly, Bob has measurement settings on his measurement apparatus that take on the values either B0, which we were calling B previously, or B1, which we were calling B prime. And his outcome we label with a Y, and Y can take on any value between minus 1 and plus 1. Now last class now the point is this scenario includes the quantum scenario where we think of the A as a vector. A0, A1, B0, and B1 are coplanar vectors. And they correspond to directions on which we do a Pauli measurement. The direction of an up-down measurement of spin. But we're not restricted to that paradigm. This is true of any theory which makes predictions about the outcomes of the measurement, whether it be classical probability theory, classical mechanics, Liouville mechanics, quantum mechanics, or some bigger theory that we haven't specified. All we're saying is that this is what the theory provides us, and this is what the experiments provide us. Now what we're interested in is a quantity S. So we have a quantity S, which we define as the expectation of A0, B0 plus A0, B1 plus A1, B0 minus A1, B1. So we defined what these expectations meant experimentally. So operationally, the meaning of this object, AI Bj, is equal to 1, the limit as n goes to infinity of 1 over n, sum over I equals 1 to n of x n. What did I call this last time? Oh, I see. That was my mistake. Of xi, yi, where it's understood where n is the number of trials for which such that Alice chose AI and Bob chose B sub j. So in other words, I should probably index n with ij, in which case this I now is problematic. Let me call this nij, and let's change this index to L. So the point is the total number of experiments, the total number of repetitions or runs is n equal to sum over ij and ij. So we collect, we do the experiment capital N times. Alice and Bob haven't communicated because they're space-like separated. Then later on we collect their lab books. We look at each experimental run where Alice chose measurement direction AI and Bob chose measurement direction B sub j. And then we take that subset and we calculate this object. So of course, as n goes to infinity, as for finite n, we're only going to have an estimator of this, but we can make that arbitrarily good, arbitrarily precise. So that's the operational meaning of this. Quantum mechanically, in QM, as I mentioned last class, an object like this corresponds to the trace of some preparation rho against sigma dot AI, sigma dot B sub j, or here A and now these are vector quantities. I'll just leave that implicit notationally. So this is the quantum prediction. This is the experimental value. And of course, we find that quantum mechanically we're going to violate a bound. So what is the bound? So now the CHS inequality is that S is less than or equal to 2 and greater than or equal to the square minus 2. Okay, here it's sufficient to consider the right-hand side of that bound, that s is less than or equal to 2. So remember, the goal is to make reasonable assumptions about the kind of physical properties that determine these correlations, and then to show that they aren't tenable, that the experimental result violates those assumptions. So we consider a model where the expectation of AI Bj is equal to an integral over some variables lambda, which are determining either probabilistically or direct functionally the outcomes. Okay, so remember, I found this notation a little bit confusing, so let's just make sure we're on the same page. Right? Remember that we use A and B to label the correlation function. Well, this quantity, you can call it a correlation function. It's a slight abuse of terminology, but it's basically that. So we're using A and B, which are the measurement directions, to label the correlation function. But the correlation function is actually a correlation between the outcomes, x and y. Right? So we're actually taking the product of the outcomes. So x can be plus or minus 1. Or sorry, x is anywhere in the interval 1 to minus 1. Y is anywhere in the interval 1 to minus 1. We take the product of the two outcomes that Alice and Bob recorded in their notebooks when we calculate the experimental value. Theoretically, we imagine that this is the average x and y. So for a fixed lambda, we calculate, for a fixed lambda, there's some probability of getting an outcome x and y, and we weight the products by the probabilities that are determined in this model. Now this model is insufficient to derive this bound here. So now we're going to make it a locality assumption. We assume, due to locality, that the probability of getting outcome x does not depend on what outcome Alice got, and it also does not depend on what Alice's choice of measurement was. Sorry, x is Alice's. The probability of getting x does not depend on Bob's outcome y or on Bob's choice of measurement, because that's happening in a space-like separated way, or whatever other reason you want to invoke the independence. We assume due to locality that we can factorize the probability of xy conditioned on these quantities is equal to the probability of x conditioned on ai and lambda, and the probability of y conditioned on b sub j and lambda. So this is generally recognized as the key assumption that's violated. Note that we're conditioning on lambda. So the point is, all of the relevant information is contained in lambda. And I'm having this argument with my former master's student right now about what exactly this assumption means, but let's not go there now. It's a mathematical assumption, and we can discuss it as a follow-up. Now let's define S to be equal. Let's let's tease out the lambda dependence by doing this. So S lambda is now defined implicitly. Then, as a consequence, of the factorization assumption, here, let me just write this out. Then S lambda is equal to sum over ij ai bj. And then we'll add a lambda on the subscript here. So hopefully, yeah, here. So now I'm defining ai, the expectation of ai bj in terms of averaging over lambda. Well, let's not average over lambda. Let's define the integrand of that integral over lambda as this object here. So this is defined now implicitly. I should be clear from, yeah?
So one of those terms is some other minus.
Right. So how can I do that? Can I do -1? No, that's not going to be possible.
I just wanted to make sure I'm something.
Yeah. You're right. So here, ij equals. Okay, fine.
I just went to the I times j my work because
I times j. Yeah. Thank you. Perfect. Thanks for catching that. Okay, good. So, so the key point is that as a consequence of the factorization assumption, we get ai b sub j lambda is equal to the sum over xy probability of x given ai lambda times the probability of y b sub j comma lambda, which then, of course, now this dependence on x and y products out. So we get essentially an expectation of ai sub lambda, times an expectation of bj sub lambda.
The -1 to the ij doesn't work if we're assuming that I and j are 0 and 1. Because you'll have two negatives, right?
no.
0.
Oh, yeah.
0 is
No, it'll work.
0.
Yeah. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0.
And then 1. Sorry. Yeah.
Yeah, we're good. Okay, so Andres was asking yesterday about the argument I gave. How did the factorization assumption work in? Factorization buys you this. You go from here to here. Now, in some sense, these guys are not independent variables because they both codepend on lambda. But nonetheless, we can write this factorization.
So you're saying there's no correlation between them despite the fact that they're dependent on the same variable?
They're independent conditionalized on lambda.
Yeah, they're independent conditional on lambda is the right way to say it.
Okay.
If we don't condition on lambda, then they become dependent.
Okay. So fixing a lambda, then they're independent.
Yes. So then we have, I guess I should write it up here, S lambda is equal to, let's just write it out in full, A0, B0 plus A1, B0 plus A0, B1 minus A1, B1. Oh, whoops. Well, I forgot to include my, We have A0, B0 plus A0, B1 plus A1 B0 minus A1 B1. Okay, so here's the trick. Now, of course, we recall that each of these guys, AI and B sub j, each of these guys belong to the interval -1 plus 1. Then we realize that S of lambda is equal to A0 times B0 plus B1 plus A1 times B0 minus B1. So now let's just derive an upper bound on S lambda. And we can use a symmetric argument to get the lower bound, but we don't have to worry about that anyways. But just so you know, you can derive the lower bound via the same technique. So now, how do we upper bound this? Well, the first term, the quantity in parentheses has some value. What's the maximum value of the quantity in the parentheses? Well, the maximum value of B0 is plus 1. The maximum value of this term is plus 1. So the maximum value of the quantity in parentheses is 2. The maximum value of A0 is 1. So that means that the first term is definitely less than or equal to B0 plus B1. Absolute value. And what's the largest contribution we can get from the second term? Well, the largest value is when B0 is plus 1 and B1 is minus 1, which would be 2. And then A1 at most can give us a plus 1. So the biggest contribution from the second term is also 2. And more importantly, it's whatever the maximum contribution is given by the absolute value of this combination. In other words, we can drop out the dependence on A0 and A1, just assume they're plus 1. So let's just assume they're at their maximum values. In which case, we can set this inequality. Now, because we have an absolute value here, we could actually write this either way. We could write this as B1 minus B0, B0 minus B1. It doesn't matter. So without loss of generality, let's just take B0 to be greater or equal to B1. If B0 is greater than or equal to B1, then we can replace this with just B0 plus B0. And we can replace this with what? I'm just wondering what the step is here. Somehow I lost it. Well, let's just write it out. So if we assume that, then this is upper bounded by S lambda is less than or equal to Jeez, this was clear to me last night. Why am I losing this?
But if we assume B0 greater than B1, then you can take the absolute value from the whole expression down. It's upper bounded by 2 times B0, which is upper bounded by 2.
You can take the absolute.
But this is going to give us 2 times B0.
Yeah, but the term in the right,
you've got
if
this
B0
is
is
down
give
front
us-
and then 1 plus or minus something.
if B0 is greater than B1, you can take off the absolute value. Because B0,
Yeah.
B0 bigger than B1, the average both, it's positive, right? B0 bigger than B1 is positive. I can take off the absolute value. If you don't want that, then
Yeah, that's fine. But what I want to get, here's what I want. What I want to show is this.
doesn't matter, it's not-
And we can also assume that these are all positive.
Absolute value.
Sorry. Why can we assume that? Without loss of generality, we can assume that B0 is greater than B1, and we can also assume that B1 is greater than or equal to 0, because if B1 was less than or equal to 0, then we would just swap their roles. So we get the same expression. So that means we can assume B1 is greater than 0. Right, that's the key. So now if we assume that B1 is greater than 0, then, how the heck? All right, so this should be clear to us. Okay, so this is the conclusion we want. And now I just have to remember what's the one argument I'm missing. So this term would give us 2b0 on its own. If we just crudely bounded b1 by b0, we can upper bound this as twice b0.
Maximally that would just be 2b0.
So someone sees this?
If you're considering
You can just drop the absolute values because of all those
Exactly.
assumptions.
I mean,
And then
if they are all
the
positive,
B1s can't.
Oh, then
You're
they
gonna get
cancel.
rid of
Right,
that.
thank you. Okay. Thank you. All right, good. So, right, so we can drop the absolute values, and then we get b0 plus b1 plus b0 minus b1, so the b1s cancel. And then we get, thank you. All right, I knew this was hidden in there somewhere. All right. Then, okay, there. We'll put QED. Okay, so that's now what's the maximum value of B0? Well, the maximum value of B0 is plus 1. So we deduce S of lambda is less than or equal to 2. Okay, great. So that's our bound. And then, of course, quantum mechanically, QM saturates the inequality S. Sorry. So hence, and in particular, this implies if we average over lambda, then S not conditioned on lambda is also less than or equal to 2, since it's an average over a probability density function. The fact that each term in this average is less than or equal to implies that the average is less than or equal to 2. So quantum saturates the inequality to square root of 2 using the singlet state. And some particular choice of measurements, which I gave you last class. So one of our assumptions has failed. It's either the assumption that there is a reality or the assumption that reality is local. And that's why this is interesting from a quantum foundations point of view. It tells us something very deep about the nature of reality. Okay, so now I want to talk about those other topics, but I'll take some questions.
So when you say the assumption that there is a reality, that's the lambda, that's the hidden variable.
Yeah, then we can talk about physical properties, and we can assign a variable to describe them.
Other than just talking about measurements.
Yeah, other than just saying, yeah, operational outcomes are all that exist, that those operational outcomes are connected to some underlying physical properties that we could give a mathematical description for.
Deterministic.
I mean,
No, notice there's no assumption of determinism here. The whole point, I mean, what CHSH did, that Bell's original proof assumed that the outcomes in this hypothetical scenario with the hidden variables were determined by the measurement setting and lambda. But here what we've done is we've allowed the outcome x to depend only probabilistically on the physical variables lambda and the choice of measurement. So we have not assumed determinism.
if you assume, if you make the assumption of locality, you also need to have the outcome be deterministic, because otherwise you're not going to get perfect anti-correlation.
Can you repeat that, please?
If you assume locality, you then need to have the outcome depend in a deterministic way, because otherwise you will fail to get perfect anti-correlations.
Oh, you mean to saturate this inequality, you
No, if
need
you want to
determinism.
reproduce quantum results, you have to get you must have the deterministic dependence on lambda, because otherwise you won't get perfect anti-correlation. Because
I'm not
if-
familiar with that.
Because so you say you have lambda and the outcome depends on lambda, but only in a probabilistic way.
Right.
Then you might sometimes measure up on both sides.
Yeah, you
because
won't get,
can't-
right. I see. So to reproduce other aspects of the quantum results.
Yeah.
So here we're just trying to reproduce one property, which is this S quantity. But
Yeah.
there are other experimentally verifiable features of quantum theory. Yeah, that sounds very plausible to me. I believe that.
That's true.
But it's important from a logical point of view to show that we can drop the determinism assumption and still demonstrate a conflict with quantum mechanics, because then that shows that the faulty assumption is not determinism.
I'm having a little trouble actually seeing why the step we took of factorizing the expectation represents locality, because it seems like it's saying the outcome of Alice's measurement is not conditioned on the measurement setting that Bob has chosen, which seems like it ought to be true, but there ought to be some dependence on the, which seems like it's true even in quantum mechanics, but the difference is that there's a dependence on the measurement that Bob actually gets, on the outcome of his measurement.
Well, the point is that we imagined that the parameter lambda could predispose a particular outcome for Bob when he measures in this direction. But that information is already included on the other side as well. So the point is that whatever information you gain by knowing Alice's outcome or Bob's outcome based on the choice of measurement in lambda and actually seeing the outcome, that information is already encoded in the conditions we've written for the other side. So if we didn't condition on lambda, then yes, the outcome you get. So there's this example of, James has this example of the urn, which I was just discussing with my student Victor, my former student Victor Veach. So the idea is that James' urn example is the difference between physical independence and logical independence. So if I have an urn with red and white balls in it, and I choose a ball and I don't look at it, now I go and I choose a second ball, so I'm choosing without replacement. So you take the ball out and it stays out. I make a second choice, I get a ball out, it's red. Suppose all I knew was that the initial distribution of balls was 50-50 red and white. Now the fact that I got a red ball on the second outcome gives me information about the probability that my first outcome was red or white. It's no longer 50-50. It's more likely it was a white ball, because now there were more red balls in the bin left over. So clearly, what outcome I got on my first choice can't depend physically on the outcome I got with my second choice, but it depends logically on it. But here the point is we're not conditioning on lambda. We're saying, well, I don't know what the configuration of the balls in the bag were, in the urn. I don't know which location I chose from. If I write down the specification of where all the balls were and encode that information in lambda, and lambda also includes where I reached into the urn and took the ball from, then we already know exactly what ball I got. That's determined by lambda, and then the choice, B sub j is where in the urn did I grab the ball from. Lambda is where were all the balls for each color. And so clearly, whatever I learned from the second choice no longer has any logical or physical effect on the probability of which ball I got on the first draw, because I put lambda in there to make sure all that information was already available. So lambda screens off the logical dependence on the outcome. So the beautiful thing about Bell's theorem is that every time you look at it and go over it, you learn something new that you hadn't seen before. There are so many subtleties involved in this kind of a construction that it's a very, very deep result. The assumptions are very subtle to understand conceptually. And so, if you're interested in this topic, I'm sure this will come up again in Lucian Hardy's Quantum Foundations course later in the term. And I'm sure you'll have a chance to explore this in more detail there. OK, so now let's turn to a discussion of from non-locality to non-local games. So a bunch of computing scientists got interested in quantum information and had all kinds of interesting insights. So basically, the idea of a non-local game is to take this experiment and turn it into some game, a game in which having access to entanglement is a resource. So here's our game. We have two players, Alice and Bob. And a referee. So now the referee asks questions to Alice and Bob. The referee can ask Alice one of two questions, and the referee can ask Bob one of two questions. Alice and Bob are not allowed to communicate. So you can think of it as a game show where each one is in some magnetically shielded box, or you can think about them being space-like separated. But we allow them, we describe the rules of the game to them in advance, and they're allowed to confer in advance and decide on what their strategy is going to be to win the game. A shared strategy. So the referee asks Alice a question. Her question is A sub I, which belongs to the set +1, -1, or 0 and 1, doesn't really matter. And asks Bob a question, B sub j, which we'll just label the questions as +1 and -1. The key point is that because they can't communicate, Bob doesn't know what question Alice was asked, Alice doesn't know what question Bob was asked in each run. Okay?
Is the set of questions the same? They can be asked. So like, there's only two questions that can be asked, so they're the same for both of you.
Yeah, the questions are labeled 0 and 1.
Okay, so they're-
So Bob and Alice are asked the same.
Oh, sorry,
type
1 and
of
-1.
The question type is same. I mean,
No,
by
so-
+1 and -1, you mean this? Bob and Alice can be asked the same question but different.
Yeah, the question +1 can be, what's your favorite color? And question -1 can be, what's your favorite number? Okay? But each answer has two outcomes. So for the favorite colors, they can only choose between red and blue. And for the favorite number, they can only choose between pi and square root of 2. Okay? So whatever the questions are, it doesn't matter. The point is, Alice and Bob's goal is to give the same answer.
To give the same answer.
Right. In the first game. We're going to do 3 versions of the game. The first version is easy, the second version is easy, and the third version is impossible. Yeah.
Here your questions are like your set of measurements. I mean,
Yeah, so the question is a choice of measurement
okay,
setting.
so in this case, wouldn't it be that ask the question AI and the outcome is plus or -1? Then there.
The questions are drawn uniformly at random, independently at random for Alice and Bob. The key point is that Alice and Bob do not get to know each other's questions. That's the communication. This is the locality assumption. And Alice and Bob must answer X is 0 or 1 and y is 0 or 1. You know, whether this is 0 and 1 or plus 1 and minus 1 is totally irrelevant. I'll probably mix it up several times. In fact, in my notes, it's 0 and 1, so maybe I should stick to 0 and 1. Sorry to do this to you guys. That's a 0. That's a 0. See, the great thing about information theory is that 0 equals minus 1. Okay, now, so now Alice and Bob can use any resource they have access to decide how to answer. They know what the question is in that run. They know what their shared strategy is. But Bob doesn't know what Alice was asked or answered, and Alice doesn't know what Bob was asked or what Bob answered.
So, Joe, sorry, I have a quick question. So, are 0 and 1, do they label the two questions or the two answers?
Well, 0 and 1 label the questions, and they label the answers as well.
Oh.
So they mean something different, right? So, okay.
So,
In here, well, maybe that's why plus 1 and minus 1 was better, but then we still share plus 1. These are just labels, right?
okay,
So AI refers to the question, what's your favorite color?
yes. And there's two possible outcomes.
Sorry, plus 1 for A. So what's your favorite color? What's your favorite number?
Yes.
From the favorite colors, I can choose red or blue.
Okay.
And for the favorite number, I can choose pi or square root of 2.
Okay.
So these are labels.
Would it be possible to have two different labels? Yeah, it just gets confusing. We have two different labels then? They just look
You can see.
No, you can't. You can't have different labels.
They can
Okay.
simply
I just wanted
decide
to
what answer to give.
on the answer to 0 can be.
Well, okay, good. So this
So
is
are-
great.
are
This
the-
is great. Here's game 1. You guys actually get to figure this out together. I'm not going to give you the answers.
They
So here.
can
Are the
decide
two
a
X
strategy
answers the same as the two Y
beforehand
answers?
and decide what answer to give when asked.
Just patience, grasshoppers. Okay? Now here's the deal. So they did a pilot of the game show, and then when they did the pilot, they realized that they weren't doing it right. So here was the pilot. Okay, so the pilot is game 1. And then they said, oh, we're not going to do this. Everyone wins all the money. Okay, pilot. Game version 1. Here's the challenge. Is this. So this is what Alice and Bob know this in advance. They know that so Alice and Bob want to give the same answer if the question is the same. If the questions match, so they're both asked what's your favorite color, and they want to give differing answers if the questions are different. So if Alice is asked what's your favorite color, and Bob is asked what's your favorite number, and we've labeled these with 0 and 1, then Alice should give 0 and Bob gives 1, or Alice should give 1 and Bob gives 0. When the questions differ. Okay. I'll give you 1 minute. Who can figure out a strategy so that they win all the time?
Are we sharing Belgium?
I'll give you 1 minute. Don't ask me. At 1 minute, I'll see what you guys say.
So, Joe, do they know from the beginning which are the questions they're going to be asked?
Questions are in random. You have no idea which
The questions are drawn independently at random in each run.
Yeah, I mean, but do they know before?
What type of
Zero and one.
Which are the questions they're going to
question
be asked?
0 or
Yeah, the questions are labeled 0 and 1,
So, but
and
they
the
know-
answers are labeled 0 and 1.
Okay, but both Alice and Bob know from before
Yes.
what are the questions.
Yes.
So
The easiest way is to use
Use opposite answers.
So they can decide beforehand that if you're asked this.
Don't talk to me. The minute isn't up yet. Talk to your colleagues.
Depending on whether it's question 1 or 0, you apply a nonlocal case, and then you give the answer.
Yeah, but it's much more simple. For question 0 to question 0, which also to get the question plus 1.
Yeah, you get that.
Question 0.
So I guess you know what 0 on the question, right?
You don't even need to filters or anything.
Oh yeah.
I'm sure you will for one of the others.
Yeah.
Always pick the different.
So they can just decide just one and say they have this person like this.
Okay, the minute's up. How many of you know the answer? About half? You have the honors.
Each of them, they answer the question with the question, or the bit corresponding to the question.
So solution 1 is they decide in advance to use this strategy. X, Y equals AB.
What is 0? What is here?
So if they're asked question 0, they answer 0. If they're asked question 1, they answer 1. That way, if they're both asked 0, they both answer 0.
Is that the other way around with the notation?
What is your favorite color? What is your favorite color?
I'll use words.
No, sorry, I meant, shouldn't AB be on the left, logically?
Oh.
But it doesn't, it's equality.
What? It's inequality. Man. All right. So yeah, so they can answer based on the question, or they can answer based on the opposite of the question. They can have x, y equals, 1 minus a, 1 minus b.
That's why 0.
What? So look, so the point is they have to decide in advance. So if they don't come up with a strategy in advance, they're not going to win all the time. But if they decide, okay, let's use strategy 1, they'll win all the time. If they decide on strategy 2, they'll win all the time. If they don't plan in advance, Alice might try strategy 1, Bob might try strategy 2, and they're toast. All right, so the point is if they plan, they can win every game. Now the network said, oh, this pilot is crazy, we're going to lose all our money because it's so easy for people to win this. So let's make it harder. They say now challenge the second version of the pilot is the following game. Now this time, Alice and Bob must have different answers if the questions are the same. And the same answer if the questions are different. Okay, you have 30 seconds. How do they do it?
Just take the negative. The negative.
One has strategy 1, the other one has strategy 2.
Right, exactly. So Emily just said it. Basically, Alice uses strategy 1 to assign her answers to the questions. Bob uses strategy 2. So in this case, they both use 1 or they both use 2. To resolve this scenario, one of them uses 1 and the other one uses the other, and then they'll always win. Okay, so they both use and here, Alice uses 1 and Bob uses 2 as the assignment rule. This is their assignment. Their answer is assigned based on the question, or vice versa. And then the network says, look, we're going to lose our shirts. People can win this all the time if they're like, moderately intelligent. They'll figure this out. They'll win every time. Okay? So, maybe that's not a no-go theorem for the show. But certainly, if they had psi students on the show, they'd be in trouble. So let's make it a little bit harder. People have to lose sometimes to make it interesting. So now challenge number 3 is let's say they have to do the following. In this case, Alice and Bob must give the same answer for all scenarios except if they're both asked one, in which case their answers must just agree. I'll give you 30 seconds. What's the optimal success probability?
3/4.
Wow, you guys are good. Okay, optimal success probability is 3/4. So they can't win all the time. So in particular, an easy way to saturate this bound is to just always have the answer the same, and then when you happen to be both randomly asked the 1-1 question, unfortunately you won't win that case. But you win 3/4 of the time, which is pretty good. Not great. So proving that this is the upper bound is something you can just think about in the shower or something. Okay? Now, is all of this time we've spent talking about hidden variables and locality and entanglement, is that useful for anything? Okay, well, it's useful for at least one thing, which is winning at this game show. Okay? So, now that might not be the most compelling argument I've ever given you.
I will get you.
But I think what it gives is some insight that there's some kind of practical upshot to all of this. Okay, so now suppose Alice and Bob happen to be grad students at IQC. And so they actually build devices which create entangled photon pairs, and they have some way to store these photons in their phones. Their phones are off in the sense that the radio is off, right? They're on airplane mode for their phone, okay? Because otherwise they're breaking the rules. And besides, they're electromagnetically shielded, right? But before they went to the game show, they both prepared thousands of singlets, Bell singlet states. And each of them has 1,000 electrons stored in their ion traps, which are now, this is 2017, so they have little ion traps inside of their iPhone 8, okay? Or I'm sorry, their BlackBerry, their
Don't worry, none of us can afford BlackBerry.
So, okay, this will be edited from the video, this last so here's the question. The question for you is, show that Alice and Bob who have quantum memory in their phones can win cos squared pi over 8 of the time, which is approximately equal to, who knows this, 0.853. Okay, and I'll put an exclamation mark there. All right, so that is, I think, a very cool way to think about Bell's theorem. So you can get lost in the algebra here and the nature of conditional probability, and it's all okay. Well, I don't really know how significant this is. But look, here's a concrete scenario where you can prove exhaustively there's no strategy for which they can win at this game more than 3/4 of the time. But given access to Bell singlets and the ability to measure their half of the Bell singlet, so they choose their measurement axes as, A0, A1, B0, B1. So when Alice is asked question 0, she measures along A0. When Bob is asked question 1, he measures along direction B1. And each time they're asked the question, okay, I'll do that measurement, and then they just answer according to what the quantum outcome tells them. That's their entire strategy. Do what quantum mechanics tells me to do, and then they win a fraction of the time that's greater than allowed using only classical phenomena. All right, so if that doesn't blow your mind, I don't know what will. But anyways, so there you go. All right, so now let me talk a little bit about entanglement as a resource. So from the quantum information theory point of view, the idea is to think about entanglement and non-locality as resources. I mentioned already that a resource arises in the context of a restriction. So this is the resource theoretic perspective. We impose a restriction on what we can do. If the restriction is LOCC, which means I have local operations in classical communication, then the resource is entanglement. And if I impose and so I've already described what that is. If I impose a restriction called LOSR, which means local operations and shared randomness. So I'm allowed to share randomness, but I'm no longer allowed to communicate. So this is more relevant to the game show we just described. Alice and Bob can't communicate, so entanglement is not the right resource to characterize what helps them, because they're not allowed to even communicate. But here, if they're not allowed to communicate, but they're allowed to share information, and particularly here they say shared randomness, then the resource is non-locality. So we now understand that non-locality and entanglement are slightly different concepts. Not all entangled states can be distilled to Bell singlets and things like that. So we have bound entangled states. And then here there's just some recent work. Very recent work has shown that all entangled states can help violate some Bell type inequality. So here, this is a result. This is a result by who's the first author again? Check my notes. So it's Liang, Doherty, and the first author is Massans. So I don't understand this work deeply, but it's very interesting, and it's on my list of to-do things. So I'll just mention it to you. Liang and Doherty. This is a PRL from 2008. And then a more direct proof is given by Buscemi in a PRL in 2012. So the key idea is we start with some given some state rho that does not violate a CH-SH inequality, there exists a sigma that is entangled I'm getting my quantifiers wrong. There exists some rho that does not violate a CH inequality such that for any sigma, so this I should say this first. For any sigma that is entangled, so let me just start with this. For any sigma that is entangled, there exists some rho that does not violate a CH-SH inequality such that rho tensor sigma violates a CH-SH inequality. Sorry, I started writing this backwards. So that means that somehow all entangled states are useful in the context of some non-local game scenario.
So sigma will violate CH-SH on its own?
No, so the point is there are some entangled states which don't violate CH-SH. So an example is the Werner states. You can find some class of states such that you vary a parameter, and there are some entangled states, so they're entangled by our formal definition of entanglement, but they can't violate any CH-SH inequality. So for any such entangled state, for any entangled state at all, including ones that on their own aren't sufficient to give you non-locality, you can always find some rho that also does not violate, that does not have non-locality as a resource in it. And together, you can construct a way to violate a CH-SH inequality when you have both those states. So each state on its own is kind of useless for non-locality, but together they're useful. So the point is somehow any entangled state can catalyze the violation of a CH-SH inequality using some other state that doesn't. We call it catalysis. This is a common term in resource theories, that there's something that's not a resource by itself, but it can catalyze other things that aren't resources to become resources. So there's a very, very rich structure, of course, which means this is great for research problems, right? This is a very rich structure which hasn't been explored in full, but there are some really neat insights that have emerged only recently about the relationship between non-locality and entanglement.
Does sigma on its own violate CSH?
No, it doesn't
Neither
necessarily.
vagina.
But sigma is entangled, so
No, you can find entangled states that
don't
don't violate
violate.
CH.
So even one
So you take two of those
that
don't violate
does not violate.
find one that violates.
And it's
so if you
rho
had an
and
entangled
entangled
pair,
state.
you're guaranteed to be violating both of them.
One
What
to
powder?
CH. I mean, if you take a bell.
So what I wrote here is that
You were talking about two states.
an entangled state, even one that on it by itself does not violate a CH-SH inequality, you can find some rho that does not violate a CH-SH inequality such that sigma and rho together do violate a CH-SH inequality. So somehow things that on their own don't seem to be non-local can actually be non-local when combined together. This is a very common theme in quantum mechanics, that the whole is greater than the parts. Yeah.
So rho is any general density matrix. It does not have to be an
There exists some rho. I haven't told you anything about its structure, except that I promise you it can't on its own violate a CH-SH inequality. So again, as I'll mention that, I'm familiar with the abstracts of these papers, but I haven't read them. But I thought I'd mention them to you because they seem very interesting to me, and it's on my to-do list.
But something here, I mean, you're constructing a state that is unentangled, right? That violates a CH-SH equality.
I think, well, these both could be entangled
Yeah,
states.
yeah, but
that
I
don't-
mean, the state that you were saying that violates a the CHS.
The combined one.
Is unentangled, right?
But it would be entangled if they were.
No, it's entangled. So rho, it would be a bipartite state, and sigma is a bipartite state. So when I write this out, this is really 4 Hilbert spaces. So there's
Yeah,
no
but I
entanglement between this space and this space, but there's entanglement between these 2 spaces and possibly between these 2 spaces, or vice versa.
Right, okay, so my ideas of bipartite entanglement here cannot be applied, right? I mean, so I can say, okay, let rho and sigma belong to 2 other Hilbert spaces. I have a bipartite unentangled state that violates CHS H inequality.
Well, you have to be clear about what spaces you're referring to, I think. So rho is, say, a pair of qubits, and sigma is a pair of qubits.
Okay.
Okay?
Qubits.
D-level quantum systems. Sorry about that.
Quantum D.
So yeah, I mean, of course, okay, I have to read the paper, but I don't know if this is relevant if you have, I mean, remember in the 2x2 case, we saw by the Perez partial transpose criterion that every entangled state could be detected. And yeah, I don't remember my theory of bound entanglement offhand. Actually, let me just say, look, I wish I knew more about this, but here are the references.
No.
And
Other thing that might related to this that is not about. Whenever I have a pure state that is entangled, I can guarantee that it violates a CHS inequality.
yes, all pure entangled states,
Okay.
yes.
So whenever I go to having a mixed state, it is not necessarily an equivalence, right? I mean, if I have a...
Yeah, mixed states is where the problems arise.
Okay.
That's where it's hard to characterize the properties, to both discover if they're entangled and to decide whether or not they are useful for violating a Bell inequality and things like that. The mixed state case is the hard case. For pure states, this is all very well understood. Yes?
So this only works if sigma is entangled. So is there a way of using that to tell if sigma is entangled?
That's very clever. Maybe. That's even more motivation to read those papers.
Okay.
Maybe. I mean, this is. I mean, as you see, 2012. That's a very recent result. So yeah. So this is fresh, and there are opportunities, I'm sure, there. Okay. Well, I was going to start Markov processes, but that doesn't make sense now. So I guess we'll just push that off to tomorrow's lecture. So, anyways, thanks again for your attention today.